Welcome students. We are back with another lesson. In this lesson, we'll discuss semiconductor. So before we discuss semiconductors, let us classify our solids on the basis of their electrical properties. So let us consider your metals. Your metals are conductors. Why they are conductors? Because they have low resistivity and high conductivity. As you can see, low resistivity and high conductivity. Next we have insulators. Insulator means those solids which do not conduct current. Now why they are insulators? They are insulators because they have high resistivity and low conductivity. As you can see, the resistivity is very high and the conductivity is very small. Now there are certain type of solids or materials which are classified as semiconductors. So what are semiconductors? The semiconductor possess resistivity or conductivity in between, intermediate means between metals and insulator. That means their resistivity, as you can see, it is greater than the resistivity of metals but smaller than the resistivity of insulators. Their conductivity. The conductivity is greater than the conductivity of insulators, but it is smaller than the conductivity of metals. So such kind of materials are known as your semiconductor. Conductor is because such kind of metals or such kind of materials behave both as your conductor and your insulator. At low temperature, they behave as insulator, and at high temperature, they behave as conductor, hence the name semiconductor. Next, before further discussing semiconductor, energy bands. Now, all the materials, they have two types of bands. One is your valence band, the other is your conduction band. What is your valence band? Valence bands are those bands which are filled with electrons. As you can see in this figure, here the electrons are filled, 2 electrons in the second, 2 electrons, 2 electrons, 2 electrons. So the highest energy level which is filled with electrons is known as your valence band, and the energy of valence band is given as EV. Next is your conduction band. Conduction band is your unfilled energy band next to your valence band. These are unfilled. Okay. So what happens when your solid conducts? When your solid conducts, what happens actually is that an electron from a valence band, which is filled valence band, move to a conduction band, which is empty band. Fine. So what is conduction band? The lowest unfilled allowed energy band next to the valence band is called conduction band. Fine. So this empty band is your conduction band having energy EC. This filled band having energy EV. Next we'll discuss about this energy gap, or also known as energy band gap. The energy band gap is the gap between the top of the valence band to the conduction band, in which no allowed energy levels for electrons can exist. Fine. So in this figure, can you see? This is your conduction this is your valence band and this is your conduction band. In this case, can you see this gap? This gap is known as your energy gap. In this energy gap, there is no allowed energy levels. If there is no allowed energy levels means electrons cannot exist between your valence band and your conduction band, and this gap is known as your energy band. What will be the energy band gap, or what is the value of this energy band gap? Then the quantity of this energy band gap, or the energy of this energy band gap, equals to your conduction band EC minus your valence band. This is your energy band gap. Fine. This empty space between the valence band and your conduction band. Fine. Coming back to our semiconductors. Now we know semiconductors are the materials which have the resistivity in between your insulator and your conductor. Your semiconductors can be further classified into two categories. One is your intrinsic semiconductor and the other one is your extrinsic semiconductor. So what is an intrinsic semiconductor? Intrinsic semiconductor refers to a pure semiconductor whose conductivity is due to the presence of intrinsic charge carriers, electrons and holes, and are not due to any impurity of foreign atoms. So what does your intrinsic semiconductor means? The conductors in which the conductivity is only due to the electrons and holes. Fine. And they don't have any impurity. This is a very important point for your intrinsic semiconductor. They don't have any impurity. Okay, these materials, they are not enhanced. They conduct by itself. Fine. So intrinsic semiconductors pure semiconductors because they are unmixed. Fine. They are not mixed with any other elements or compounds to improve their conductivity. Fine. So such kind of semiconductors are known as your intrinsic semiconductors. For example, you can take germanium. Germanium, as you can see, this is your germanium. The germanium nucleus has charge +4 and it has 4 valence electron. Can you see? 1 valence electron, 2, 1 valence electron, 2 valence electron, 3 valence electron, 4 valence electron. So a germanium atom is sharing its 4 valence electron with the 4 neighboring germanium atom. As you can see in this figure, it is sharing 1 valence with this 1 germanium, 1 electron with this germanium, 1 electron with this germanium, 1 electron with this germanium, and so on. So this germanium has a valency of 4, which is being shared by its 4 nearest neighbors. Fine. The other example you can take is your silicon. Moving on. Next we'll discuss conduction in intrinsic semiconductor. How does your semiconductor, or let us say, how does your intrinsic semiconductor conducts current? To understand this one, consider you have a germanium crystal. Fine. On this germanium crystal, we will supply energy. How we will supply energy? By increasing the temperature. Now when we supply energy by increasing the temperature. What happens? The electron at this site 1, at this point, what happens? It gains sufficient enough ionization energy and gets ionized, or it gets sufficient amount of energy and it is emitted, or it is removed from its valence bond. Can you see? This electron is ejected. So you have a thermally generated free electron. So this free electron conducts your current in the intrinsic semiconductor. Fine. Now, how many electrons will be generated? The number of electrons generated, Ne, will depend upon your temperature. It depends only on the temperature, and the number of the electron generated is given by the formula Ne equals to Ce to the power minus Eg by twice of kT. Yes, C is a constant, E is your exponential, Eg is your energy. What is your energy gap? The gap between your conduction band and your valence band. This difference in the amount of the energy is known as your energy gap. So for an electron which is at the valence band, if you supply some amount of heat to this electron, what happens? This electron becomes free and it moves to the conduction band. In the process, you get conduction in the semiconductor. Right? So Eg is the energy of the band gap divided by twice of Kb. This K, can you see this K? This K is your Boltzmann constant times T. T is the temperature which is being supplied. So the number of electrons generated thermally will be given by this formula. Now apart from that, note here, as each free electron creates one hole. As you can see, when the electron becomes free, what does it leaves behind? It leaves behind a hole. So if one electron becomes free, so one hole is created. So as each free electron creates one hole, so in an intrinsic semiconductor, the number density of free electrons, the number of the free electrons generated per unit volume is the density. Density is the number generated per unit volume is the number density. Fine. So the number density of the free electrons, Ne, is equal to the number density of the holes, Nh. What does it say? It says if one electron is emitted, one hole is created. If two electrons will be emitted, two holes will be created. So the number of the electrons, or the number of the free electrons generated, equals to the number of holes. So this is what is written here, the number density in a particular volume, this particular volume. Therefore, if we are considering it in particular volume, we won't say its number, we will say the density. Fine. So hence we are using the term number density. So the number density of the free electrons, Ne, is equal to the number density of the holes. Fine. So each is equal to the intrinsic charge carrier. So in this case, why is the current being conducted? This is conducted because due to the free electron. Hence, if one free electron is generated, one hole is also generated. This valency, we will term it as hole. Fine. So if one electron is generated, one hole is also generated. Therefore, your intrinsic semiconductor, in your intrinsic semiconductor, what are the two types of charge carriers? One is your electron, the other one is your hole. And what about their quantity? Their quantity will be equal. So the number of the electron generated, number of the free electron generated equals to the number of hole, equals to the number of hole. And both are your charge carrier of the intrinsic semiconductor. So both of them are denoted by Ni. Fine. So Ni equals to Ne equals to Nh. Next, we'll discuss about the propagation of charge carriers, how your charge carriers propagate. Okay, now for that, consider your case 1. Suppose there is an electron, you supply energy to this crystal or your material. What happens to this electron? This electron becomes free. If this electron becomes free, what is generated? A hole is generated. Fine. Now when a hole is generated, what happens is that a nearby electron sees a valency at this position. So what will happen? Makes a transition from its state to this hole. As you can see in the second figure, the electron which was at your site 1 has now moved to your site 2. Can you see this black? It has moved to site 2. Now when this electron moves to the site 2, what does it create? It leaves a hole behind at site 1. So in your electrons are propagating. Fine. Your electrons, which are the charge carrier for the intrinsic semiconductors, are propagating. But note, the holes are also propagating in the same manner. If the electron is going in this direction, what about the holes? The holes are also going in the opposite direction, isn't it? So this is how the intrinsic charge carriers propagate in your intrinsic semiconductor. So if you have the propagation of electron as well, you have the propagation of hole. So what will be the total current generated due to hole and electron? So the current I equals to the current generated by the electron plus the current generated by the hole. So IE stands for the current due to electrons and IH stands for the current due to the propagation or due to the motion of holes. Fine. Now, your intrinsic semiconductors, they have conductivity but in very less amount, which is not suitable for practical purpose. So to make it suitable for practical purpose, what we usually do is we dope. Dope means adding impurity, adding of extra material. Fine. So what is doping? The process of deliberate addition of desirable impurity to a pure semiconductor so as to increase its conductivity is called doping. So what we do, we introduce desirable impurities. Now why do we introduce impurities? To increase its conductivity. And what is this process called? This process is called doping. Fine. Now the impurity atoms added are called dopants, and the semiconductor doped with the impurity atoms are called extrinsic or doped semiconductors. So the impurity atoms which are added to your pure semiconductor, or I'll say to the intrinsic semiconductors, those added impurities are known as your dopants. Now when you add dopants to the intrinsic semiconductor, what happens? That semiconductor becomes impure, and hence we will call that as extrinsic semiconductor, or they are also known as your doped semiconductor. Fine. Now, usually there are two types of dopant. So, intrinsic semiconductor like your silicon and germanium are doped with two types of dopant. The first category is your pentavalent dopant. Now this pentavalent dopants, they have the valency 5 and they belong to group 5 elements. Okay, so the examples are arsenic, antimony, phosphorus. Take an example in this case. This is your pentavalent dopant. We have added a impurity, or we have added dopant to your pure semiconductor. What is this +4+4 valency type of material? It is your germanium. So what we have did, we have introduced a pentavalent dopant. Now pentavalent dopant, it means penta means 5. So pentavalent, valent means valency. So pentavalent means 5 valency electron elements. So what happens is that in this pentavalent, one of its electron is shared with one neighboring atom. This electron is shared with another. Here the electron is shared with the another. Here the electron is shared with the another. Fine. 4 of its valence electron are shared with the 4 nearest neighboring atom. But what about the one which is left? This unbound free electron is donated by your pentavalent +5 valency atom. So what happens if you dope with pentavalent? You get a extra free electron, and this extra free electrons helps in your conductivity. Fine. Moving on to our next type of dopant, trivalent dopant. They have 3 valence electrons. Some examples of your trivalent dopants are your indium, boron, and aluminium. Fine. So when you dope your pure semiconductor, like in this case you have +4, that means your germanium. When you dope such kind of pure semiconductor or intrinsic semiconductor with trivalent dopants. Trivalent dopants has how many valence electrons? 3. So it shares its 3 electrons with 3 nearest neighbor atom. So if it shares the 3 nearest neighbor atom, what happens to this fourth one? It does not has any electron to share with this fourth one. Hence there is a hole created. So what does your trivalent dopants donate? The trivalent dopant donate extra hole. This extra hole helps in the conductivity of your extrinsic semiconductor. Fine. So we had two types of dopant, pentavalent and trivalent. Pentavalent have 5 valence electron, trivalent has your 3 valence electron. Pentavalent donates 1 free electron, whereas trivalent donates your 1 free hole. Fine. Doping. I can classify my extrinsic semiconductors into two categories. One is your p-type semiconductor. P-type semiconductor. So what is a p-type semiconductor? When your semiconductor obtained by doping with trivalent impurity. That means the elements of your group 3 of the periodic table. When you dope it with such kind of impurity, you will get a p-type semiconductor. Fine. Now, when you dope your extrinsic semiconductor with a pentavalent impurity, these impurity means the elements of your group 5. When you dope with pentavalent impurity, you will get a n-type semiconductor. So your extrinsic semiconductor is further classified into p-type and your n-type semiconductor. In p-type we have trivalent impurity. If you have trivalent impurity, hole, and when you dope it with n-type semiconductor, that is your pentavalent impurity, that means you have a extra electron. Fine. So that's it for today's class. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So thank you.